So in the previous video, we've talked about some really interesting stuff, but mainly we've introduced the Cartesian product of two independent spaces or sets. Then, we've seen that interaction creates this new mathematical object called a point, right? And from there, we structurally interpret a set versus a relation, a mathematical relation. And we found out that there's going to be an increase in structure, the mathematical structure and relation, due to the fact that a relation has now a binary predicate, whereas a singular set, had a unary predicate. So one predicate versus double predicate, right? And that already creates new objects, new rules, and introduces things like order, because in a set, order was completely irrelevant. So we already have this increase in structure, and that was our endpoint on our previous video. Now I like to talk about functions, because I feel like this progression naturally leads to functions, right? So, because it's a function is not something completely separate from a relation, right? Because a function is a special kind of relation. So you could see function as a subset of a relation. It's within that region, right? So this is the R, and that would be F for function, right? But now, since we're introducing a new, subset, or again, this new area or boundary, that means that we would have to introduce a specific constraint, because again, from the previous video, Cartesian product. Right. So we've created a Cartesian product using two independent sets, correct? And the Cartesian product create this new nice space of points of the coordinate planes. Of the coordinate objects, and we took a specific region, and that specific region is called R, a relation. From that Cartesian product, let's call that A times B. And now I'm telling you that, hey, there is a special kind of a relation where we would have to take the subset of the R, right? So that means that for a function, we need to introduce a different constraint, right? And that constraint is very specific, okay? And it is for every input in A, there must be exactly one output in B, which is associated with it. So every input, where A is part of A, set A, there must be exactly one. So exactly one element from B associated. And then such that we would have the pair, B comma B, A comma B, sorry, right? So this is obviously still a relation, but it's a very specific kind. And this new print we introduce must be present for every single function, okay? So as we're progressing, right? As we're progressing from sets to, predicates, creating this subfield or boundary within the space, from sets going to the Cartesian product and creating points and then relations and functions, we're not really abandoning the previous structure that we've had through the membership conditions, the logical predicates. We're adding constraints and organizations to it, basically. We're never forgetting about the previous structures, right? So a set distinguishes possible objects. It creates this subspace that is different from the universal set, U. Set is just this little region, right? And a product coordinates these possibilities and allows us to take possibilities from each set, from two sets, simultaneously and independently. And a relation constrains those coordinated possibilities because like maybe I'm interested in a specific relation, not all of the relations, not all of the possibility spaces that the product creates, which is completely fair. And a relation introduces a very specific, a directional rule inside that relational structure, right? So that this, in simple words, again, means that for my input values, A is the input at this point, I can't just do like this, right? For every input value, I need only a single map, right? I need to either go like this or like this. I can't do them simultaneously. That's simply not allowed in a function, but this map allowed in a relation.